Alright guys, so in this video I wanted to talk about permutations with restrictions and permutations with repetition. So let's start with permutations with restrictions. So sometimes you might come across problems where there is some sort of restriction in place. So I'll use an example. Let's say we have the first 5 letters of the alphabet: A, B, C, D, and E. Okay. Now, you're asked to find out how many permutations you can take 4 of these letters, right? So I'll draw 4 positions and reorder them, right? An example of a restriction would be saying that you had to take out a D, and the D had to be in the first slot. So this must be D, for example. So what would we do in that case? Well, let's start by thinking about what the formula for a normal permutation example would be. We know that we would take x factorial, which would just be the number of elements in your first group, divided by x minus y factorial, where y is how many positions you have, or how many letters you're taking out in this case. So in this case, what is this going to be? Well, it's going to be 5 factorial, right? Because we have 5 elements in this initial group of elements. And then we take 5, subtract 4 factorial, right? And that's actually just equal to 5 factorial divided by 1 factorial. And that's the same thing as 5 times 4 times 3 times 2 times 1. Okay. Now that's just in this case. And that's assuming that there is no restriction, which clearly there is a restriction. So how are we going to integrate this restriction into our formula? Well, if we know that this first number must be D, then there's no point in assuming that this first position can be different letters. This first position will always be D. So the only positions that we need to concern ourselves with are these 3 positions. And we also need to consider the fact that D will not be in any of these positions because it's in this position. So really what we can now do is we can just say that instead of 4 positions, we have 3 positions. And instead of 5 elements in our initial group, we now only have 4 elements, because this D right here is not going to be included when we're thinking about what elements can be in these 3 positions. So let's plug in our new numbers. So we're assuming that we only have 4 elements. Now we're going to divide this by 4 minus 3, because we're not even thinking about this first position. So that's equal to 4 times 3 times 2 times 1. And that is the same thing as 24. So there are going to be 24 different ways that we can take out 4 letters where the first position must be D. Okay. Let's do another example. Let's say we have the letters X, Y, and Z, and we're picking 2 of them. Actually, we're picking 3 of them. And our restriction is that Y and Z must always be together in this order. So Y and Z must be together in the order Y then Z. So Z cannot come before Y. So how are we going to deal with this? Well, we can think of YZ as its own element. So instead of x, y, z, we can just think of it as x comma yz. So where yz is its own element. The reason we can do that is yz will never, y and z lose their independence because they've sort of merged to form this single element. So this merge of two elements can be thought of as one element because it will always be in the same order and these two elements will always be together. Now, do we still have three positions that we're taking? No, we actually only have two positions now. The way that we're thinking about it, if yz is its own element, then we only have two positions. Because we only have two initial elements. Okay. So how are we going to deal with this? Well, we can just use our formula. We can say, okay, we have two initial elements, right? We're dividing it by 2 minus 2 factorial, right? So that's just the same thing. Oh, sorry, 2 factorial. That's just the same thing as 2 factorial, which is equal to 2. So there are two ways that these letters can be rearranged if yz must always be together. What about the case where yz does not necessarily have to be in the order yz? So they always have to be together, y comma z, but they can also be in the form of zy. What would we do then? Okay, so just to make that clear, this y comma z, they must always be together, but they can also be in the form of zy. Well, we can do this the exact same thing as last time, okay? So we can take 2 factorial. So we're thinking of yz as just one element. You'll see why this works in a second. And then we can divide it by 2 minus 2 factorial, which gets us just 2, right? By the way, if this doesn't make sense at all, then you should probably go back to one of my previous videos on permutations. Yeah. If the factorials don't make sense at all, you can do some. You probably need to do some research before you watch this video. Research on factorials. So just look up factorials. You should find some information. But actually, I'll give a quick lesson on what a factorial is really quickly. Factorial basically means, so for example, if you had 5 factorial, it would just be 5 times 4 times 3 all the way to 1. And if we had 2 factorial, that would just be 2 all the way to 1, which is just 2 times 1. 0 factorial is actually 1 as well. But if you want a more detailed lesson on that, you could probably do some learning on your own, because this video isn't meant to explain what factorials are. But anyways, as I was saying, we can basically just say that 2 factorial, we can do the exact same thing as before, and now we have this number 2, which represents how many permutations there are, assuming that y comma z must always be in one order. And then we can take this number, 2, and then we can multiply the number of permutations, assuming they're in that order, by the number of different ways yz can be reorganized, which is actually going to be 2 factorial, because there are 2 elements that are being put together. So why does this work? Okay, why does this work? Well, before we were basically assuming that y comma z, when they're put together, they will always be in this order. But if we wanted to take into account the fact that yz can also be in the order zy, then what we would need to do is we'd need to multiply those number of permutations by the number of different ways yz can be rearranged. And that works because, well, I'll write it out. If these are our 3 positions, before, when we were always assuming that YZ must be in that particular order, these were our two combinations. XYZ, that's a combination, and then YZX. Those are the only two, permutations that work when YZ is together and it's always in the order YZ. Okay, but we can multiply the number of permutations possible here by the number of ways that this YZ can be sort of rearranged in order to get the total number of permutations when we're not assuming that YZ will be in that particular order. Okay, so we multiply it by 2 factorial, and we talked about why you just take the factorial of how many numbers there are, how many elements there are, to get the order of something, or the number of different ways you can rearrange something. But basically, whenever you take the factorial of something, of a number, that's the number of ways you can reorder it. So this y and z here, you can reorder it 2 factorial ways. So now you have a whole new set of things. So you can go x, z, y now, right? And you can also go z, y, x. So if you just saw what I did, instead of x, y, z, it's x, z, y. I just switched these 2 around. And now we have 4 permutations. So what I did was I multiplied it by 2 factorial because I wanted to see how many different ways y, z could be rearranged. And the way to get that is basically just take the number of positions. So in this case there are 2 because there are 2 elements, y and z, factorial. So 2 factorial would be the number of ways y, z can be rearranged. And if we multiply how many permutations we had before, which is just 2, by that, we get all of our permutations possible, not assuming that YZ must always be in that order. Okay. Now let's talk about, so those are some examples of restrictions in permutations. Now let's talk about some, repetitions in permutations. Okay. So let's say you have the letters A, B, C, D, and E. Okay. Yeah, so A, B, C, D, and E, and you're taking out, and you're looking for the number of ways you can rearrange these. We've gone over this before, so I won't talk about it too in depth, but a repetition would be if you had something like A, B, C, D, and then just another D. So you have 2 of the same element. So how would you deal with something like that? Well, let's use our formula. So let's say we have, this is to calculate it assuming there is no repetition. I'll talk about how we can calculate it without repetition, with repetition in a second, but this is assuming there is no repetition. So you would do 5 factorial, divide it by 5 minus 5 factorial, because essentially what we're doing here is we're just taking 5 numbers from these 5 numbers and seeing how many different ways we can rearrange it. And that's the same thing as 5 factorial. And that's equal to 5 times 4 times 3 times 2 times 1, which is the same thing as 120. Okay? And 120, so that's how many permutations are possible when there is no repetition. But what if there is repetition? Well, we can actually divide it by the number of repetitions there are. So we can take 120, we can divide it by the number of repetitions there are, factorial. So in this case, 2 factorial. Now why does this work? Well, you can imagine if, let's say we ordered it like this, A, D, B, C, D, okay? Before, when we just got the 120, we were assuming that these two D's were different. So we were counting A, D, B, C, D twice because we were assuming that D was a different letter than D. So for example, we were saying like A, D prime, B, C, D. So we were saying that these two D's were different elements, but really they're just the same. They're the same thing. So A, D, B, C, D should be the same thing as A, D, B, C, D. So right now, I'll just use a prime to make it clear the difference between the D's. But for example, if we got A, D, B, C, D, then A, D, B, C, and then D prime, and then we had A, D prime, B, C, D, those would be considered different permutations, but really they're the same permutation. There shouldn't be a prime here. And I'm just using the prime to make it clear that what D's which. So we have to divide it by 2 factorial because we're getting rid of all of these redundant permutations. Let's do another example like that just to practice and solidify it. So let's say we have sort of the same example, except instead of A, B, C, D, D, we just have A, B, D, D, D. Okay? How are we going to do it now? Well, assuming there are no repetitions, we know that there are 120 permutations, right? I just calculated that before. But how do we calculate the number of permutations with repetition, right? With these repeating D's? Well, if we were to go back to this sort of example, let's say we had A, D, D, B, D. That's what we got. These 3 D's could be rearranged in 3 factorial ways, okay? And we want to get rid of all of the redundant ways that of A, D, D, B, D. So let's say this is D prime, this is D prime prime, okay? If there was another permutation that happened and it was in this order, for example, these two would be considered different permutations. And there are going to be 3 factorial of these, okay? There are going to be 3 factorial different ways to re-represent A, D, D, B, D using just those D's, changing those D's around. So we have to divide it by 3 factorial because we're getting rid of those redundant D's. Now, how would we deal with multiple restrictions or multiple repetitions? And actually, since I just finished the repetitions, I am going to start with repetitions. So what if you have multiple repetitions? What I mean by that is, what if we have, for example, something like DD, EE, FF, right? Something like that. Well, like before, so we're dividing, before we divided by the number factorial, the number of repetitions sort of factorial. But now, what we would have to do is we'd have to divide 120, or actually no, it's not 120 in this case. The number of permutations, assuming there aren't any repetitions, and we'd have to divide those permutations, assuming there are no repetitions. So kind of like we did up here, we assumed there were no repetitions, even though there were. And now we have to divide that by, in this case, 2 factorial times 2 factorial times 2 factorial. So what I did is I divided by 2 factorial because there were 2 d's, then I divided by 2 factorial again because there were 2 e's, then I divided by 2 factorial yet again because of the 2 f's. So in order to calculate permutations with repetitions, what you need to do is take permutations with no repetitions, so assuming there are no repetitions at all, then divide that by however many repetitions there are of one element factorial, then divide it again by however many repetitions there are of another element factorial, and then so on until you've accounted all of the elements that are repeating. So in this case, we divided by 2 factorial 3 times because there were 2 repetitions of D, E, and F. If there were, for example, 2 D's, 3 E's, and then 4 F's, what we would need to do is divide by 2 factorial, then divide by 3 factorial, then divide by 4 factorial. So again, just to calculate permutations with repetitions, we divide permutations with no repetitions by however many repetitions there are of one element factorial, divided again by the next element's repetitions factorial, so on until you've completed all of the repetitions and accounted for all elements that are repeating in your elements, in your initial group of elements. And that will equal the actual number of permutations with repetitions. Just to recap, because this is pretty much the end of repetitions in this video, the reason we divide by the number of repeating elements, so in this case we were using letters, so I'll use D as an example. There were 3 D's, so we're dividing by 3 factorial. We're doing that because for every single permutation, there are going to be 3 factorial times too many, because we're assuming that the D's are different letters. When we first took our, when we calculated our 120 permutations, we were assuming that the D's were all different elements, but really they were all one same element. And if we got, and I just did these primes to sort of clarify the difference between the D's when I was showing you this example, but this right here, this is your first D, okay? This is your second D, this is your third D. If it was reordered in some way and we got A and then the second D first, and then the first D next, and then the last D last, those should be considered the same permutation. But they weren't because we were assuming that these D's were all different elements, but really they were all the same elements. They were all the same element. They were just copies, right? They're all D, right? So in order to sort of remove that assumption that these are different elements, what we had to do is we had to divide by 3 factorial. So what did that do? Well, dividing by 3 factorial would get rid of all of these redundant sort of recombinations of the D's. So there are going to be lots of these recombinations of the D's. Maybe you get A, D, no prime, and then D prime, and then B, and then D prime prime. That's yet another way to re-express this where the D's have all been mixed about. And again, with our 120 permutations, we were assuming that these were all different permutations. But really they're not. They're all the same permutation. Yeah. Okay, so let's move on to restrictions, multiple restrictions. Let's say that we're given the example with A, B, C, D, and E. And we're taking out 5 of these. Okay? And D must always be together. Okay? And C must always be at the front. Okay? So this must always be C, and E must always be together. What are we going to do now? Well, now we just have to account for both restrictions. So like we did in the past one, let's just start with C, okay? C on its own. We're going to say, well, we can pretty much just disaccount this first position, right? Because this C is always going to take it up. So we're just going to assume that there are four positions only. We're also going to discount C from the number of elements we have because we know that it will always fill this first position. So we can just say that we only have 4 elements. So now we have 4 elements. So we factorial that. And we divide it by 4 minus 4 factorial, right? Okay. Are we done? No, we're not. Because we still have to account for this DE. So DE will always be placed there in that particular order. Well, we can just assume that it's its own element. So we can say that we have A, B, and then DE, right? Because we're not even including C, because we're just forgetting about it entirely because it's always going to be at the front. It's doing its own thing. So now we only have 3 elements, okay? And how many positions do we have? Well, we basically only have 3 positions. We're going to assume that there are only 3 positions because if DE takes up, so for example, if we were using our 4 positions, right, or our 4 positions, if DE was here, that's basically just saying, we can basically just say it's taking up 1 slot, right? Because they're always going to be together. So we can just think of it like we only have 3 positions. Okay. So now let's plug it into the formula. We have 3 factorial divided by 3 minus 3 factorial, which equals 3 factorial, which equals 6. Okay? So there are 6 different ways A, B, C, D, and E can be rearranged, assuming that C is always in the first position and D, E are always together in that order. Let's do one more restriction example. Note that you do have to be quite versatile when you're dealing with these problems because they can vary a lot, and you might need to think of new ways to solve these problems. These are only some of the different problems. These are just examples of some of the different problems you might come across. You should probably be prepared for a large variety of different problems. But that require you to think in different ways and sort of move things around a bit. But anyways, let's say we have A, B, C, D, and D, and F, and we're taking these and we're filling up 6 positions. Okay? Our restrictions are that C and D must always be together, so they're sort of glued together, and they're always in that order, and E and F are also glued together in that order. Okay, so how are we going to deal with this? Well, let's just assume that there is only one restriction right now. So we're just going to forget about EF right now. We're just going to concern ourselves with CD. Okay, so assuming that is a restriction, we can just think of CD as its own element, right? A, B, C, D, and then E and F, right? And now we can assume that we have 5 positions, because if C, D are put together, it's only going to be 5 positions. Okay, now let's think about E and F put together. So now it's going to be A, B, C, D, and then E, F. Let's erase this. Let's erase this as well. Okay. Let's say, yeah, so how many positions are we going to have now? Well, 1, 2, 3, 4, because we're filling up how many elements there are, right? So there are only going to be 4 positions. So now we can plug everything into the formula. There are 4 elements, right? We're dividing it by 4 minus 4 factorial. That's equal to just 4 factorial, which is equal to 24. So there are 24 different ways A, B, C, D, E, and F can be rearranged into 6 positions, assuming that C and D are together in that order, and E and F are together in that order. So that pretty much concludes this video on restrictions and repetitions. Note that you will probably come across a variety of different problems, so you will need more than just the skills that I applied in this video to solve them. You will probably need to be a bit creative with how you solve these problems, because they will require a versatile set of solutions. Okay, so that pretty much concludes this video. Thank you.